welcome to today's webinar. This webinar is hosted by Jen and sponsored by Elogen. Today's topic is rapid synthesis of full-length, high-complexity clonal genes. Thanks so much for being here. I'm Uduak Thomas, Senior Editor with Jen, and it's my pleasure to serve as your host for today's webinar. Let me introduce today's speakers. We have Dr. Galit Meshulam Simon, Associate Director for Commercial Applications at Elogen. We have Dr. Matt Diener, Staff Scientist in the Product Development Department at Elogen. Before we get to their presentations, let's start off with some background on today's topic. Constructing plasmids that contain complex full-length genes can be cumbersome. The iterative construction process, which involves stitching smaller gene fragments together, is longer and more error-prone for complex structural elements such as inverted terminal repeats or long repeats. Errors in the initial building blocks or the construction process accumulate, necessitating the screening of multiple colonies for each construct in order to identify a sequence-perfect plasmid. So in this webinar, our speakers will present recent innovations in DNA synthesis that enable fast, accurate synthesis of long, complex plasmids, and they'll share data that compares novel and conventional approaches. During the webinar, you'll learn about Elogen's proprietary cell-free cloning technology for highly accurate fragments for plasmid construction, and how it is used for building and expressing long and complex pathways, such as the carotenoid biosynthesis pathway and additional reporter genes. So what are some key takeaways from today's webinar? You'll hear about the robust Infinia plasmid DNA process. You'll also hear about some of the challenges of building long and complex biosynthetic pathways with conventional gene synthesis methods. And you'll also hear some case studies that highlight the benefits of switching from small error-prone fragments to long, accurate linear DNA to build large, complex constructs. At any point during the event today, if you have a question, you can enter it in the Ask a Question panel located on your screen. All right, let's get started.
Thanks, Uduak, for the introduction, and thanks everybody for joining us to this webinar to learn more about Infinia plasmid DNA and how rapid clonal gene synthesis powered by our high-accuracy Infinia linear DNA enables rapid and reliable supply of complex and long genes. We will dive deeper into scientific feature of this new product and show data from use of Infinia plasmid in few examples application. Shipped as fast as 10 business days with the gene lengths up to 15 kb, Infinia plasmid DNA can help to eliminate the reliance on internal cloning and accelerate workflow in many segments of synthetic biology. Elogen, based in San Francisco Bay Area, was founded in 2017 by Matt Hill to address the growing need for scalable, versatile gene synthesis. Elogen's cell-free technology overcomes the limitations of conventional gene synthesis platforms that rely on cumbersome cell-based methods. In these methods, short gene fragments are assembled and cloned to correct synthesis error and to obtain yield. Our production platform is highly scalable and adaptable to meet the growing demand for gene synthesis in all fields of synthetic biology, and also in healthcare applications like cell and gene therapy and mRNA vaccines. And this is without significant investment in internal resources and infrastructure. A little bit about our technology. So Elogen cell-free cloning technology overcomes the limitations of traditional cell-based methods. We synthesize near-clonal quality double-stranded linear DNA that is longer and with higher complexity than offered by conventional gene synthesis provider. It can ship within a week. Early in 2023, Elogen launched Infinia linear DNA, providing researchers with double-stranded linear gene fragments of DNA up to 7 kb, which is all NGS verified. All of our linear DNA is produced using our cell-free process and shipped globally as soon as 6 to 8 business days, all from our facility in San Francisco Bay Area, United States. The speed, length, and complexity of Infinia DNA has set the bar for next-generation gene synthesis. Instead of paying more and waiting weeks for long and complex DNA to be cloned in a plasmid, Infinia DNA gives you up to 7 kb high-complexity DNA with NGS verification without a wait. On the right-hand side of the slide, you can see our extremely low error rate of 1 to 70,000 per base, which is average estimated accuracy of 99.999%. This is much lower compared to other linear DNA providers. In general, with our Q-spec and this level of accuracy, we expect 80% of the gene synthesized to be full length, and out of that population, 95% should be sequence perfect. At this level of quality, it's typically enough to pick 1 to 2 colonies to get sequence perfect gene. After launching Infinia linear DNA product and increasing the complexity of the genes, we discovered that many of our customers are actually using it to simplify their cloning workflows. Instead of assemble several small fragments into a vector for cloning, they only had to assemble 1 or 2 of our longer fragments. This improved their assembly success rate and saved a lot of time. As plasmids are widely used in synthetic biology and remain the dominant final format of DNA in many workflows, and since our mission at the end is to take the DNA build process off the hands of our customers, we decided to launch Infinia Plasmid DNA to deliver our long and complex DNA in a cloned plasmid format for those who required plasmid for their downstream applications. So I would like to talk a little bit about the differences between conventional build approach to the Infinia Plasmid DNA approach. The conventional gene synthesis relies on a long and cumbersome build process, which is starting from oligos that are assembled into short blocks around 200 base pair, and those are stitched together to make low quality, relatively short, typically lower than 2 kb DNA fragments. To make longer DNA, multiple fragments are subcloned and assembled into plasmid vector and cloned and sequenced and again. So as most fragments are subcloned because the sequence error rate is high, typically around 1 to 3,500 per base. So subcloning of those fragments is needed because it's important to isolate the sequence perfect clone. So after those small fragments will be cloned, transformed, and sequenced, the process will repeat itself for the final product. So overall, this is a lengthy process, which is time-consuming, costly, and error-prone. While building long genes, this process can take weeks and sometimes even months if you're waiting for really complex fragment to get built. So how is it different with Infinia? With Infinia, because our linear DNA Infinia can provide you up to 7 kb near clonal quality fragment, which is being assembled pretty quick in 6 to 8 business days, you can basically skip all this cumbersome process of subcloning. And we are doing now the assembly into the final vector, transforming and sequencing to get you the sequence perfect molecule. With Infinia Plasmid DNA, we're actually taking on that step for our customer, and we are doing the final round of cloning. And since we produce the linear fragment in 6 to 8 days, we can ship our cloned plasmid with insert as long as 15 kb as fast as 10 business days. As Matt will show you later, the majority of our plasmid are shipped in 10 to 15 business days, and they can save weeks of time when compared to conventional approaches. We offer plasmids in 2 flavors, standard complexity and high complexity. When you look at longer inserts over 3 kb in length, our speed and pricing, especially with high volume orders, are very competitive. Right now, we offer a library of standard backbones to select from, but for customers with larger order volumes, we are open for onboarding and building custom vectors. So just reach out to our sales team if you are interested. Turnaround time and price are not affected by vector type, and also NGS verification is included at no additional cost, even for complex structural elements like ITRs. Here we are showing what are submission acceptance criteria, which is what you will see when you're going to our portal. And what I wanted to emphasize here is really our acceptance criteria for complexity that are higher than typically our other vendors. And you can see the overall GC content, the high and low GC content. And what we also hear a lot from our customers is that sequences that will not be accepted by other vendors are accepted by Eligen as a standard complexity. At this point, we want to talk a little bit about the plasmid build process analysis, and I will let Matt take it away from here.
Thanks, Galit, for handing it over to me. So I am, again, the technical lead for this project. And so I'm just going to talk through some of the data that we generated during the course of development and verification of the plasmid build process. So to test this, we tested 107 distinct plasmid sequences. So these come from 3 distinct sets. So there are 44 sequences from the AdGene public database. So just pulling plasmids off of AdGene that correspond to different vector backbones. There are 30 sequences that were submitted by beta test customers, so real sequences that we know customers want. And then we also modified 33 of the AdGene sequences to evaluate different assembly factors for our build process. And so I'm showing here sort of the breakdown. We have 7 backbones, as Galit mentioned, and we get pretty good representation of AdGene and real sequences, customer sequences across all the backbones. Most of the assembly factors were tested just in our standard high copy PUP19 amp vector. The overall performance looks really good, as you can see. So I'll call out the backbone here, the total number of plasmids that we synthesized from end to end, essentially all the way from DNA synthesis through plasmid cloning. And then the success rate in that backbone. And what you'll notice is that we were able to synthesize every single AAV plasmid that we attempted with very high efficiency. We think that our ability to synthesize AAV, or to essentially synthesize the insert and clone into the AAV vector, comes from our proprietary ligation-based process for assembly. So that gives us an improvement over sort of conventional homology-based methods for or homology-based assembly methods such as Gibson assembly or NEB HiFi or anything like that. We also show here the overall percent success rate based on the complexity of the insert. So we made 81 plasmids that had a standard complexity insert. I mean, 95% of those from end to end. And even with a high complexity insert, so things that are really high GC, low GC, we're able to, and also with a lot of secondary structure, we're able to make 92% of those. And what I'll call out is that the turnaround time does not vary significantly based on the complexity. So an average of 11 business day turnaround time for the standard backbones or standard inserts, and then 12 for the high complexity inserts. So if we wanted to, I think this slide really shows the distinct advantage that Eligen has in terms of making really long plasmids. And so what we're showing here is on the y-axis, we have the required clones to pick. So this is the required number of colonies you'd have to pick to be 95% sure that you're going to pull out a sequence-perfect plasmid. And then on the x-axis, I have insert length. And so if you use just a simple model to calculate the number of clones you need to pick, if you had as input a block or a fragment with a 1 in 3,500 base pair, or 1 in 3,500 per base error rate, what you would see is that the number of colonies that you need to pick to actually be able to pull out a sequence perfect clone exponentially increases as the insert length increases, right? So on average, if you have an insert that's 15 kb, that's going to have on average 4 errors in it, right? And so it's simply impossible to pull out a sequence perfect clone, and thus you need to subclone your inserts individually before putting them into the final plasmid. However, with infinilinear DNA, because our error rate is 1 in 70,000, on average, every single 15 kb insert is sequence perfect. And so you can see here, the number of colonies that we needed to pick to pull out sequence perfect plasmids actually does not vary significantly as you go from 5 to 15 kb. Also wanted to show the relative performance based on different insert complexities, just to show that the plasmid process or the plasmid product we're offering in Elegant now can handle all of the complexities that the Infinia process can handle as well. And so if you look the performance, again, the number of clones to pick, we don't need to pick that many colonies to get sequence perfect plasmids as a function of overall GC content. So even at high GC content, but between 55 and 65%, we only need to pick a couple of clones to get a perfect plasmid. That's the same thing for the low local GC. So if you look at the GC content in a 100 base pair window, so things like promoters and terminators, we really, even at the really, really low GC content for those sequences, we'll pick only a few colonies and pull out a sequence perfect plasmid. And the same thing for the most part for the high local GC as well. There does seem to be one sequence that we had to pick quite a few colonies for, but in general, we were able to pull out a majority of really high local GC plasmids with the same number of colonies as the kind of standard local GC. So it appears that the plasmid assembly is robust to GC content, and so we can handle anything that you can currently get through the Infinia process, Infinia linear process. You can also get as a plasmid. Also wanted to look at things that may influence plasmid assembly. So again, I called out Gibson and NEB Hi-Fi as two potential homology-based methods. So those sort of rely on the chewback of a strand, one of the strands, to produce single-stranded DNA that anneals two stitch fragments together. And so those can be kind of those can be affected by significant secondary structure in the insert, as well as repetitive sequences that can cause fragments to misanneal together. So we wanted to look at how the maximum hairpin stem length in the insert. So we have a range of 0 to 40 base pair hairpins to see how that affected our assembly process. And you can see again, even for something that had between almost a 45 base pair hairpin, we only need to pick a couple colonies to get a sequence perfect plasmid. And then the same thing for long repeats. You can see that even up to 1 kb of repeats within the plasmid insert, we only need to pick a couple colonies to get a successful plasmid. So clearly this again highlights our ability to handle really complex inserts because of our ligation-based assembly method that does not rely on the production of single-stranded DNA. Another slide to showcase this. If you look at our success with AAV plasmids, again, we were able to synthesize 100% of the AAV plasmids we attempted during our verification process. And I'm showing here sort of a representative plasmid, just we picked 6 clones per plasmid. And you can see here that the coverage plot that we generate, and this is an IGV, is very, very even across the AAV2 ITR sequence, which is kind of notorious for producing either entire deletions of that sequence or small deletions because of the secondary structure. And if you zoom in on the AAV2 ITR sequence, you can see that we get very, very even coverage across that sequence, and there does not appear to be any deletions across any of the 6 clones we looked at. And another thing I want to call out as well is that this entire sequence verification process is complementary and included with the plasmid product itself. So no paying extra to verify your AAV2 or your ITR's sequences. We get this entire kind of sequencing coverage for free based on the long read sequencing that we use for plasmid verification. One other feature too is the turnaround time. So obviously there's sort of, because we can do really, really long plasmids between 5 and 15 kb of insert the same as under 5 kb with our process. This means is that the turnaround time is largely insensitive to length and complexity and is consistently between 10 and 22 business days. So if you look, I'm showing here the insert length on the x-axis. So this is the length of the synthesized insert that went into one of our standard backbones. And then I'm showing the overall turnaround time for the process on the y-axis. And you can see that there's very little relationship between the insert length and the turnaround time. And that's also true for the complexity. So I'm showing here on the bottom panel standard complexity and on the top panel high complexity. And you can see, I also have this broken out over here with these 2 histograms. You can see that there's really not much of a difference between the standard complexity and the high complexity turnaround times. So all of them are between 10 and 22 business days. And again, this is because we sort of do the hard work up front and we produce really low error rate DNA, and that makes it really easy to just insert that into a plasmid, pick colonies, and know that they're going to be sequence perfect. Again, on the turnaround time, so if you actually compare our performance against that of another vendor, everything, all the red points here are a competitor's quoted turnaround time through their portal. You can see, as we discussed, right, the turnaround time as a function of length, it's a pretty strong relationship, right? As you get above 5 kb, and really you see this inflection point once you get above 6 and 7 kb, where the quoted turnaround time starts to explode, right? And that's because of the fact that you need to subclone individual fragments when you are working with high error rate DNA. But you can see for Elogen, we're showing here the minimum and maximum turnaround times that we would provide based on length. And you can see that you get the same turnaround time between 3 kb that you would at, we didn't actually test all the way up to 15 kb for this study, but I would say that the turnaround time is very consistent all the way up to 15 kb. So, at least twice as fast as what we were quoted by another vendor. The other thing too is the turnaround time is also not really affected by complexity as well. So that's another factor that can affect vendors' quoted turnaround times as well. So Elogen, I think the takeaway is that our turnaround times are very fast and is very insensitive to length and complexity. And so I will hand it back to Galit to talk about some of the actual applications downstream of the plasmid synthesis process.
Thanks, Matt, for your explanation about Infinia plasmid process. And what I would like to show now is our few examples of how we can use our plasmids and about their functionality. So as a first proof of concept for our plasmid, we wanted to demonstrate the functionality of widely used reporter genes. And we picked M cherry and M neon green, and we synthesized them in-house using Elogen process and also outsourced for a vendor. Once we got those plasmid back, we transformed them and looked at the functionality and the expression of those two reporter genes. As you can see in this slide, the expression level of our Infinia plasmid versus the vendor's plasmid is typically is virtually identical. Once we had that in hand, we wanted to try another application. And to do that, we choose to test the plasmids in the application of cell-free in vitro transcription translation reactions. So TXTL or CFPS reaction offer many advantages and overcome the limitation of cell-based expression systems. They allow to use in vitro system to express protein from DNA template. So we took the two reporter genes that we talked about in the previous slide, M cherry and M neon green, and we also added another one, which is purple wild type or chromoprotein purple. And we tested their expression in this cell-free system, which, and in this case, we used the TXTL Pro cell-free expression kit from Arbor Biosciences. As you can see in this slide, the expression level from these plasmid templates is basically great. And in the case of M neon green is very comparable to the positive control, which is provided with the kit itself. We tried here two codon optimization versions, and you can see one is higher than the other, but that's acceptable. Also, we got a nice fluorescence for the M cherry and very nice absorbance for the purple wild type. We can also see that we tried that with the initial mini prep that we got when we transformed our plasmid once and when we did it again. So the plasmid is stable, it keeps expressing. So these examples showed us that there are plasmid not that we're just able to synthesize them, they are really functional in those applications. So the next step was to take advantage on the accuracy and speed for building long and complex pathways. And to demonstrate that, we picked lycopene and beta-carotene. So these are two important metabolites, and there are many studies that are demonstrating their overproduction in many different hosts. with that, these are long and complex pathways, so to build them typically takes long time and it's a very cumbersome process. So we were able to assemble and get the lycopene pathway in a pretty short time of 13 days, and we choose to express it in a low copy vector because we saw that this will enables better accumulation of the metabolites. We also outsource that to a vendor, and what you can see here is that really we are getting very nice expression of the lycopene, and it seems to be higher than the expression in the vendor's vector, which is a high copy a number, which we were forced to that selection. The second example is really for the beta carotene pathway. As we said, long and complex pathway. This is 8.8 kb, and we cloned it in two vectors. In this case, we choose a PAC19, and we choose the high copy number, and we choose the low copy number. And you can see that compared to the control, we are getting very nice expression. In this case, we got higher expression even with the higher copy number plasmid. We also got expression from the vendor in parallel. It seems that expression from our plasmid is higher in this case. So overall, I think in these examples, we can demonstrate that we've been successful in synthesizing functional reporter genes, and more importantly, long and complex pathways. In summary, Infinia plasmid DNA enables the synthesis of long, complex clonal gene as fast as 10 business days. All our plasmid are NGS verified, and we are competitive on pricing. Our robust production supports gene blends up to 15 kb with 20 to 80% GC content and secondary structures and repeats. Those plasmid are ideal for synthesis of long and complex pathways. But it's really about the speed, the complexity, and the accuracy of the genes. So the plasmid are available now for ordering in our e-commerce portal, and please reach out with any question or comment. Thank you very much for joining us for this webinar.
Many thanks to our speakers for an informative and interesting presentation. We're going to begin the Q&A session in just a few moments. Please submit your questions if you haven't done so already. Before we start the Q&A, a reminder that this webinar will be available to view on demand in the next 24 to 48 hours. Please share the link with your colleagues who might not have been able to join us today. And welcome everyone to the Q&A session for today's webinar. We are delighted that you have joined us. As always, if you have a question at any point, please go ahead and enter it in the Ask a Question panel on your screen. Matt, Galit, thank you so much for your presentations. Those were really, really great. I'm going to jump in and get started with the first question that I have for you already. Matt, this one's for you. How do you QC your DNA?
Yeah, so currently we use long-read sequencing for QC of both linear fragments that we ship as Infinia linear and plasmids. So we evaluated a range of sequencing platforms, and for our methods, long-read sequencing was the best option because it allows us to see the entire plasmid molecule as compared to something like Sanger or Illumina that only gives you short chunks of the plasmid that you have to sort of stitch together. Another major benefit is it allows us to sequence the regions with high secondary structure, such as ITRs. I know I showed that coverage plot earlier, where we get really, really nice sequencing data across something that normally can form really, really high secondary structure that makes it hard to sequence. So also allows us to sequence repetitive sequences as well. So we can handle complexity really well with long-read sequencing.
Wonderful. Wonderful. Thank you so much. Next question I have is also for you, Matt. What makes Elegant plasmids different from other vendors' plasmids, if you could speak to that?
Yeah, so touched on it a little bit during the presentation, but we are using our patented cell-free technology to actually synthesize the linear fragments that go into our plasmids. And we synthesize those with a very, very low error rate, and we can synthesize up to 7 kb of linear insert. That allows us not to have to subclone to purify out the errors before we stitch them into the final plasmid. And that means that we can assemble in a few days and get high accuracy clonal genes, whether or not the plasmid is 3 kb or 15 kb. So that's the first difference. The second difference is we're also using a ligation-based method for our assembly. That can be different from other vendors that use homology-based methods like Gibson or NEB Hi-Fi or any other kind of method to use homology to stitch fragments together. Those methods produce single-stranded DNA that can form significant secondary structure, and our method does not. So we can handle stuff like ITRs. It makes us also really robust and successful with high repeat regions and other really elements that form significant secondary structure. And again, I'd like to call back to the fact that we were able to synthesize every AAV plasmid that we attempted in our panel. So it seems to be working quite well.
Excellent, excellent. Thank you. And speaking, staying on the topic of complexities, which you've started to touch on nicely, are there any specific combinations of complexities that are particularly challenging for your technology?
Nothing has really stood out. We've highlighted some of the complexities like hairpins and long repeats that challenge methods to produce DNA, and we're finding that our technology performs well to the limits that we published. Especially if you're familiar with ordering our InfiniLinear DNA, our plasmid process can handle any of those complexities that you would submit for InfiniLinear. Actually, Infinia plasmid DNA can actually handle some sequences that are too complex even for InfiniLinear, because of our proprietary assembly algorithm, which allows us essentially to synthesize the insert DNA in such a way that we can ameliorate some of the complexities that you would normally experience with our InfiniLinear synthesis. And again, because we have our really low error rate, we can ship complex sequences at essentially the same turnaround time that we can ship our standard sequences.
Excellent, excellent. And I just want to take a moment at this point to remind the audience that if you have a question, please feel free to enter it in the Ask a Question panel that is located on your screen. Moving on to the next question I have, and I think this one's going to be for you again, Matt. Which vectors can I use?
Yeah, so currently we have a list of 7 standard backbones. So we have sort of high and low copy cloning vectors, PUC and PBR. We also have 4 AAV vectors with different promoters on them. So kind of the most commonly used promoters that are used in gene therapy. And then an saRNA backbone for self-amplifying RNA work. So we also have another AAV vector, by the way, that has just the ITRs in it if you want to test your own promoter as well. So you can download information on each backbone from our website, elegenbio.com. So we've got a plasmid map and the sequence in there as well. So
excellent, excellent. Next question I have, and Galita, I think this one's for you. Can I submit sequences in my own vector?
Right. So yes, that's maybe following Matt's answer. So at the moment we are using standard backbones, as Matt just got the details, and you can select them from our portal. However, for customers that have large volume orders, we are open to really support either custom backbone or onboarding vectors. It really depending on the number and the volume of the backbone that is needed, the numbers of vectors and volume of backbones. So please do not hesitate to contact us. You can get really more information at info@elegenbio.com, approaching our sales team, but we are happy to hear from you and to work with you to support your needs.
Excellent, excellent. And this next question is talking about the future of the product. So, Galit, maybe you could give us a little sneak peek into some of the future improvements planned for the product.
Yes, for sure. So we are always working to improve our services and always happy to hear from our customers what do they need. For plasmid, some of the things that we were talking about was to improve our algorithms for assembly so we can support more complex sequences. We also plan to support longer homopolymers. So that's on the, let's say, the design of the sequences side. Another area that we are talking about future improvements are supporting larger scale preps and also glycerol stock. So those are some of the features that we plan to do in the future.
Excellent, excellent. And just one last reminder to our audience, if you have a question, please feel free to enter it in the Ask a Question panel on your screen. Next question I have, Matt, I'm going to I believe this one's for you. What yield can I expect from my plasmids? It's a two-parter. So second part of the question, how do you measure it?
Yeah, good question. So we provide a minimum of 50 nanograms of a low copy vector and a minimum of 1 microgram for high copy vectors. It's So there's a lot of discussion on this, but it's really common in gene synthesis and other kind of workflows to use UV-based methods like nanodrop to measure mass. However, we've seen in our hands that this can result in inflated yields due to potential contaminants that come through the mini prep process. So we measure our yield with an intercalating dye, which we think is more accurate, and it's more accurate because it's highly specific to double-stranded DNA. But if you are expecting or you normalize your process based on nanodrop, we would potentially recommend that you confirm the concentrations of the plasmids that you get with nanodrop when you receive them. But we do think our measurement is more accurate to the actual mass of the plasmid.
Excellent, excellent. This next question is another two-parter. And Galit, I think I will come to you for this one. How do you ship the plasmids? And the second part, will you support more formats in the future?
Yes, that's a great question. I know as a customer, you always want to know how will you get your product. So we ship those as a dry down in a 96 well plate. Every well passes our QC criteria. Every well contains one clone only. We have discussed other options, so that for your second question, so like 384 well plate or tubes, and we may do so in the future.
Excellent, excellent. Next question I have, do you ship to Europe or Asia?
Yes, we do. While we make all our product in San Francisco, in the USA, we ship and we are already shipping to customers worldwide. So, yes.
Wonderful, wonderful. Thank you so much, Matt and Galit, for being here and for taking time to answer some questions for us. That is all the time we have for today's webinar. But before we go, a reminder that this webinar will be available to view on demand in the next 24 to 48 hours. So please do share the link when you get it with your colleagues who might not have been able to join us today. And you can also watch the entire webinar from beginning to end when you have some more time. Many thanks again to both of our speakers for being here. Thank you both so much. I'd also like to thank today's sponsor, Elogen, for sponsoring this event. And last but not least, I want to thank the Gen Multimedia Group for hosting. So thank you, David Mosley, Reynolds Gutierrez, and Natalie Torn. And last but not least, I do have to thank you, our audience, for being here. For everyone at Gen, thank you. I'm Uduak Thomas, and goodbye for now.